Okay, good morning. Hello, hello. Pardon me for just a moment. I just realized I left my stylus. I'll be right back. Oops. One. Okay, now I'm ready. So, I don't see anybody here yet, but it looks like my mic is picking up the sound. I will assume that's true. I'm going to try to edit something on my screen for a moment. This is my first time streaming on a new computer here, so I need to adjust something real quick. If I can manage. Okay, there we go. All right, sorry about that. Now, I do see someone here now. If you could say hello, that will give me some comfort that you can hear me and see what I'm doing here, and all that. So hello in the chat. Okay, at any rate, I'm going to go ahead and start the process here in case anybody's going to watch this later. So today we're going to take a look at the Exam1 solutions. This is a Saturday morning. I'm not offended if you're watching this later instead of now. That's no problem. Today, what I want to go through is first of all the solutions, but second of all, a description of what it is, how I'm going to grade the exams. I have not begun grading yet, but I will do so probably. I might be able to get to them before I come back to you next time. That's my goal. But I do have a lot going on next week with the travel, so it might be a little bit later than that. So the way I'm going to grade, essentially, if you get an answer completely correct, of course, you get full credit, assuming you showed me your work. If you get something, if you get the wrong answer, but most of the stuff is correct, then that would be, basically all you forgot was like a negative sign, or you flipped around one number, forgot to convert one unit, something like that, a very simple mistake. Then what I'm going to do is pretty much only take 10% off. So you get almost all of the credit. And then if there's more problems than that, you have, let's say you used the wrong reactor type for a mass balance, or you completely missed a concept, but everything else was pretty much the correct process, that would be about 25% off of that problem. Now, if you have multiple conceptual problems, you used the wrong mass balance, you didn't convert any of the units, and perhaps you just really did not even set up a mass balance in the first place, or something, or you misidentified what it was the question was asking for, then you're looking at more like 75% of the credit taken away. So it will scale with how much you've shown me that you've learned. So that's my goal, is really to, as a measure of how much you learned. I'm realizing just now that my stylus, the way it's operating right now is it's being used on both screens, and that's a bit of a problem. So can show you. I'm just gonna edit this real quick, see if I can get it to only use the first screen. Okay, I think that should do it. Yeah, okay. All right, now I'm all set. Sorry about that. Okay, so that's my goal, is to use the grade to measure how much you learned. And so let's go ahead and begin. And we'll start with problem 1. And so here we have a series of 2 well-mixed lagoons. They're being used to treat wastewater from a small municipal treatment facility. That treatment plant treats 750 cubic meters per day and uses a biological reactor in the lagoon to remove BOD, so biological oxygen demand. The incoming BOD concentration is 25 milligrams per liter. The BOD decay rate decays at a rate of 0.27 per day. The first lagoon is 4 meters deep and has a radius of 17 meters. The second lagoon is 3 meters deep and has a radius of 12 meters. Okay, so let's go ahead and essentially draw our system here. We have a series of 2 lagoons. So we'll draw these as circles. It said they're well mixed. We've got a flow rate coming in, and then it flows from the one to the next, also well mixed. Got a volume for this one and a volume for this one, and the Q's flowing out. We have a concentration of this BOD coming in at 25 milligrams per liter. Which is not terribly high. The dimensions for this first one are, let's see, radius of 17 meters. That's should be radius, not a diameter. The radius for the next one was 12 meters. And both of them, let's see, no, the first one was 4 meters high, and the second one was 3 meters high. So we can calculate the volumes of, essentially they are cylindrical, so we can calculate the volume of a cylinder as the depth, or the height, times the area of the circle, which is pi r squared. So V1 here, that would be 4 times 17 squared times pi. And if we solve that, that should be 3,632 cubic meters. And V2 here should be 1,357 cubic meters. Okay, so there's our volume terms for this problem. And part A is asking us, and one thing you might note here is I went ahead and drew the system and labeled a few things that I know about before I even began to solve the problem or look at what we were trying to solve. And so now we take a look at problem A. It says, what is the BOD concentration leaving the first lagoon? That is essentially, so we still have the Q here, of course, flowing between, but that is essentially C1. So that's our first question. What is C1? And so that's where we're going to take a mass balance, and we're going to solve for C. So we can assume, since this is a treatment facility, it's operating continuously, that it has reached steady state by now. So just to be safe, you could document this and say assume steady state. That would, perhaps you'll have a problem at some point that's not steady state, and I give you some indication that it is, but you miss that, and so you assume it's steady state. Well, that shows me at least that, once you've made that assumption, if then you follow the process for a steady state system, that at least shows me you're aware of what that steady state means, even if you missed part of the concept that, something changed in the system which indicated it was no longer steady state. But there's nothing like that here. So this would be steady state. That means our accumulation term goes to 0. And so the net accumulation in that first reactor will do a mass balance on that first reactor here. So this will be no accumulation. We have some inputs, QC naught, minus the outputs, QC1, plus whatever reaction term we have, and this is a decay reaction because the stuff is decaying. This will be V1 times K C1. We know it's first order, which is why we have a C term in the reaction term. That first order is that 0.27 per day. We know it's first order because it's in per day units. So when we set this up, we can start solving 0. I'm going to go ahead and divide everything by Q. So it'll be theta 1 K C1. And then we can solve for C. For C1, I'll go ahead and move both of those terms over to the other side and then factor out that C1. So this becomes C1 equals C naught divided by 1 plus theta 1 K. And hopefully that should look rather familiar. Oops, sorry. So that should be rather familiar because we've seen that several times before. And then what we'll do from here is simply put in our numbers. That's going to be that 20 milligrams per liter divided by 1 plus, we need to solve for theta. So theta 1, that's V over Q. So that's going to be 3,632 divided by our Q, which was 750 cubic meters per day. And one thing we'll notice here is this gives us a value in days. That's good because our rate constant is in per days as well. So if we solve this for theta 1, that's going to be 4.84 days. While we're at it, we can go ahead and do the same thing, solve for theta 2. We don't need it just yet, but just to have it on hand, that's turns out to be 1.81, 81 days. Okay, so then coming back to our problem here, theta 1, that was 4.84 days times 0.27 days to the minus 1. Those units will cancel, and we'll be left with some form of milligrams per liter, and it's going to be a decrease because on the bottom it's in value that's greater than 1. Okay, so once we put in those numbers, we should find a C1 equal to 10.8 milligrams per liter. Let me leave that there for a moment. So that would be our final answer. That is, for part A, that is below the 20, so we are achieving the treatment. That's kind of a good thing to double check in your mind, that yes, we have treated the system as we believed we were doing. Okay, and if at any point you've got any questions, let me know. Seems like it's just you and me, and you might be a bot that's just watching the stream. Of course, I'm sure people will watch this later if you're interested. Okay, part B says, what is the BOD concentration leaving the second lagoon? Okay, so we just had the first problem where we solved for the C1 here. Now we have the second problem asking, okay, well, what's the C2? In this case, we've got V2, the same reaction, it's well mixed. And so we're going to do the same exact thing. We'll say C2, we just derived the same math, is going to be equal to 1 plus, C2 is going to be equal to C1 divided by 1 plus theta 2 times K. Given that we have those numbers from last time, that becomes pretty simple. We also solved for that theta 2 last time, and we'll just put in those numbers here, and that becomes 7.28 milligrams per liter. Okay, so that's just basically the same process, putting in those numbers. Even if you got C1 wrong, likely that same mistake will carry through anyway. But if you used this process, of course, I'm going to give you most, if not all, of the credit for getting the process correct here. Okay, so part C is next. That was, what is the overall BOD removal efficiency for the entire system? And I wanted that in a percentage. And so really what this is asking for is, what did we start with compared to what we ended with, right? That removal efficiency is going to be the C initial minus C final divided by what we started with times 100% to get it into a percentage. And that'll be that. So that's going to be 20 milligrams per liter minus that 7.28. Milligrams per liter divided by 20. And that'll be essentially 71% removal. So we get a fair bit of removal, but certainly not everything in that case. Part D will asks us, how efficient will the plant be without the second lagoon? And again, answering in percentage. So this is the same problem, just asking, okay, well, C1 minus C naught minus C1 instead of C naught minus 2. Multiply that by 100%. And in this case, that is 56.7%. So it gives us a good idea of how much of an impact that second treatment lagoon gives us. Okay, moving on to problem 2 here. We have an active construction site that's producing a large amount of sediment runoff during rainfall events. You are tasked with ensuring that the sediment particles in the runoff don't reach local streams, a local stream at harmful levels. And so it says, if a 1.5 square kilometer area receives 5 centimeters of water over the course of 8 hours, what would the flow rate of the runoff be in cubic meters per second? So really, we're just taking this part is just a geometry problem, just to say, okay, we have some plot of land. This is the construction site. It's receiving some amount of rainfall. It's a very small amount of rainfall. Well, 5 centimeters is not actually that small. That's a fair bit of rain for one day. Oops. And so you might have conceptualized this as a drawing of a small rectangle. Rectangular box here, where you have an area of 1.5 kilometers squared and a height here of 5 centimeters. So the first task really is to identify what volume of water this is, and we'll just take that volume divided by time, and that's our flow rate, right? So the time was given as 8 hours, and the volume here we can calculate, and we want to calculate that in cubic meters per second, and we need time in so we need time in seconds, and we need the volume term in meters. So that's going to require a little bit of conversions here. So let's take this the area here and say the area is going to be 1.5 square kilometers. We can multiply that by, what I'm going to do here is say 1,000 meters per 1 kilometer, but I'm going to square that term, and you have to square outside, you have to square the number, that conversion number, as well as the units. So that will give us 1,000 square meters divided by 1 squared kilometer squared. That'll get rid of the kilometer squared units and give us a term with just meters. We also have to do the same thing for the centimeters. We have to multiply this by 5 centimeters, and of course it is in 1 meter there are 100 centimeters. That'll get rid of those terms. So once we do that, excuse me, that's for the volume. I just did the area there. So this is the area, and what I'll do is say the volume includes that 5 centimeters, so the volume is going to be, let me grab a calculator. So for the 1.5, that's really 1.5 times 10 to the 6. And then we'll take that 1.5 times 10 to the 6. We're going to multiply it by 5. So that would be 7.5 times 10 to the 6. And then we're going to divide it by 100. So that yields us 7.5 instead of times 10 to the 6. That'll be 7.5 times 10 to the 4th. Cubic meters. Okay, so that should give us a flow rate once we take the Q here. This is going to be that many cubic meters. We're going to divide that by our 8 hours, multiplied by the fact that there's 3,600 seconds in each hour. That'll give us seconds on the denominator, and it turns out this would be 2.60 cubic meters per second is our answer. So just a bit of geometry here for that part of the problem. So next we are told to design a retention pond to act as a sedimentation basin, which must be able to handle a flow rate of up to 2 cubic meters per second and remove all particles above 20 micrometers in diameter. Question is, how much land area must be set aside for the sedimentation pond? And here we have to assume the water temperature to be 15 degrees Celsius and the particles to have a density of 1.55 grams per centimeter cubed. And the question asks us to answer in square meters. Okay, so first thing to note is what we're looking for is we have that sediment, all that water that's coming off from the construction area. Got this runoff, and that's coming into a retention pond that we're setting up. And we need to set up that retention pond with some area, and that's what we're trying to solve for, is what area do we need if the flow rate that we're designing for is 2 cubic meters per second. So what I did here was I made it so that it didn't really matter if you knew the area from last time. You didn't have to have the correct calculation for last time, because we're going to design it based on a 2 cubic meter per second flow. Chances are that 5 centimeters over 8 hours, that's what, maybe 2 or 3 inches in 8 hours. That's probably pretty heavy rainfall, and maybe you didn't need to design for that heavy of a rainstorm. Okay, at any rate, this is our problem now. Our Q is 2.0 cubic meters per second. Our particle diameter is 20 micrometer. That's going to be the same as 2.0 times 10 to the minus 5th meters. The water temperature is 15 degrees Celsius. That means we'll have a dynamic viscosity of 1.139 times 10 to the minus 3rd kilograms per meter a second. That's from the lookup table. And we know that to design our system, we're going to be at a case where our sedimentation velocity is equal to our critical velocity. And we design our critical settling velocity in terms of Q and AB. So we can say that's going to be the flow rate divided by the area of the basin. And so when we want to solve for the area of the basin, we can simply say that area of the basin is going to be Q over that V naught, which we can find by saying Q, since V naught and Vs we're setting the critical to be the sedimentation velocity of this particular type of particle. That means when we solve, it will just end up being Q over V naught is our area of the basin. A couple other parameters we'll need here. The rho for the particle was 1.55 grams per centimeter cubed. This is going to be the same thing if you do the conversion to kilograms and cubic meters, because first of all, one cubic centimeter, you could do this in a couple different ways. You could convert directly into cubic meters from centimeters, but you can also perhaps recognize that 1 cubic centimeter is the same as 1 milliliter. So 1 cubic centimeter is 1 milliliter. So either way you go about it, this becomes 1,550 kilograms per cubic meter. And the rho for our water, the density of our water in this case, I don't have in front of me, so I need to find the lookup table. So let me pull up that real quick. Okay. So at 15 degrees Celsius, we have a density of water 999.1 kilograms per cubic meter. Okay, so that's 999.1 kilograms per cubic meter. So that gives us everything we need in order to solve our Vs here. That's G times rho of the particle minus rho of the water times diameter of our particle squared divided by 18 times our dynamic viscosity. So with all of that, That's going to go in the denominator to solve for our AB. We'll calculate this in just a moment, or we'll go ahead and do that now. I'm going to pull up Excel for this one, hopefully to make it clear. We'll say this Vs is going to be 9.81, that's our acceleration due to gravity, times the rho of the particle, which was 1550, minus rho of the water, which was 999.1. This will be multiplied by our diameter of the particle squared. Diameter of the particle is 2 times 10 to the minus fifth. All of that is going to be divided by our 18 times the dynamic viscosity of water, which was 0.001139. And I missed a hang on, I missed something. Because that number is far too large. So I think I missed, probably should have put another parenthesis there. What did I do wrong? Oh, I put E2 here, which would be 0. That should have been 2 times e to the minus 5. So 2 times 10 to the minus fifth. So what I'm going to do there instead is I'm just going to go ahead and write that out the simple way and say that's 0.12342. So that should be 2 times 10 to the minus fifth, which means we would have 4 zeros in front of the 2. 1, 2, 3, 4. And then that fifth decimal to get to there. So that should give us the correct answer. And that's going to be in meters per second. I knew that that answer was baloney because whenever we're solving for the sedimentation velocity of a particle like this in a reasonable system, the answer in meters per second is far below 1. It's 0.000 something. And so the fact that it was, tens of thousands, it's like, okay, well, that's particles moving a little too fast there. All right, so that was our answer here would be then 1.05 times 10 to the minus 4 meters per second for the velocity, and that gives us an area of the basin, which is equal to, and I had this one calculated already, that is 18,968 square meters. Okay, so the next problem here is problem 3. This says jar tests are a commonly used tool to measure the effectiveness of coagulation dosing at a lab scale. Consider a 4-liter jar with a submerged stirrer for the following questions. So essentially we have a jar and a stirrer that is mixing. Now, we didn't talk directly about jar tests, but you'll very likely use jar tests when you do like an environmental laboratory. These are in just about every wastewater or drinking water treatment plant, and if wastewater treatment is making use of a coagulant, they often will use it there. But anytime you're using coagulation, these jar tests are run with some frequency to just test the parameters of the current water. If you get a rainstorm, the conditions are going to change, and it doesn't change exactly the same every time. And so to optimize your coagulant dosing, a very simple way to do it is to take a series of jars and test different doses of your coagulant to see which one works the best, and then you just use that one for the day or for the next few hours. So operators will have a good idea of the range of coagulant dosing needed, but given the daily and hourly changes in water quality, they'll be checking it to make sure they're using kind of an optimal amount. Okay, so it's a batch system. You have it stirring. It's a jar essentially, and this is at room temperature, 20 degrees Celsius. So the question says, if the stir is powered by a motor that supplies 0.07 milliwatts of power, what is the mixing intensity of the water in the jar? So we're asking for that G, which is in per seconds. We have a formula for this, which is the square root of the power divided by the dynamic viscosity of water times the volume of that jar, or the basin. And the power here needs to be in watts. So since this was 0.07 milliwatts, that's going to be 0.00, let's see, this would be out to, so milliwatts being 1/1000th, so we need essentially 3 more zeros than we had right there. So we need 4 zeros total, 7 watts. And then on the denominator here, we have a unit that's in kilograms and meters, so the volume needs to be in cubic meters. So for our volume, well, let's go ahead and get our viscosity here. The volume, we'll just write it here as well. The viscosity here is going to be, if we take the lookup table, 1.002 times 10 to the minus third kilograms per meter per second. Our volume is going to be that 4 liters divided by 1,000 cubic meters. So we'll put those two in here. 1.002 10 to the minus third with watts, and then with kilograms, meters, seconds, and over here meters. That all those units should be consistent because watts are essentially newtons per or joules per second, and joules is kilograms and newtons, or is in newtons, which is in kilograms and all that. So that is would be the correct way to calculate it. And so once you convert the units to make sure they're all kosher, then we should get a mixing intensity of 4.14 per second for that problem. Okay, so that would be the solution to the first part here. The next part says if there are initially 1.5 times 10 to the 7th particles in the jar, and all particles are 40 micrometers in diameter, how many particles per liter will be in solution after 30 minutes of stirring if the particles are completely destabilized? So that completely destabilized should remind us that's this symbol here. This collision efficiency is 1. The next thing to consider is we were given some number of particles in the jar. So this is going to give us an N naught, but it's going to be 1.5 times 10 to the 7th per 4 liters. That's particles. And if we want it particles per liter, then we probably ought to go ahead and convert that, and that would be, divide that by 4. So that would be 3.75 times 10 to the 7th, or 6, excuse me, particles per liter. Okay, so that's our kind of starting condition. Again, we're looking at what's happening in a stirred jar. We're doing the flocculation here, but since it's a jar and not a CSDR, then our math is going to use batch kinetics instead of the the CSDR method. Okay, the question is asking how many particles per liter will be in solution after 30 minutes of stirring. So what we want to know is N after 30 minutes. So that's particles per liter. Now, on the mass balance side of things, if you remember, we've got in that volume some change in the number over time. That's going to be equal to negative K times V to the N to the 1 power. The V's will cancel, and we can integrate like we've done in the past and say N at some time is going to be equal to N initial times E to the minus K times T. And of course, one thing to consider is the time we're given in 30 minutes. However, our mixing intensity is in seconds, so I would go ahead and convert that to seconds, or convert the mixing intensity to minutes. Either one's fine, but we'll just go ahead and multiply this by 60 seconds per 1 minute. That should be 1,800, I think. Just do that real quick. Yep. Okay, so we have that much time, and really this problem is not going to take too much else in terms of the mass balance side of things, but we need to find K, and that's a little bit involved. So K, and this is coming from our formula sheet, we know that K is equal to the collision efficiency times 4 times the flock volume, this omega term, times our mixing intensity divided by time. We have all of that except for the flock volume. The flock volume is given as the volume of one of the particles times the number of particles per volume of solution. So essentially what fraction of the total volume is in the jar is actually particles, right? The rest of the volume is water, some volume is particles. That fraction is this answer here. So that looks like N naught times the volume of a sphere the size of a particle, which is pi times that diameter of the particle cubed divided by 6. So if we calculate that, again, we have to make sure that we've calculated appropriately for the number of particles in the jar, and used that in, so we got that in particles per liter. The other thing we may want to do up front is convert that from particles per liter into particles per cubic meter, because we're going to have this diameter of the particle in a meters unit. So diameter of the particle was 40 times 10 to the, 40 micrometers is 40 times 10 to the minus 6 meters, or 4.0 times 10 to the minus 5th, right? Same thing. We would need to do that conversion, and we would also need to do the conversion so that we're using like terms here with the meters, and for the N naught, we would need to take that 3.75 times 10 to the 6th per liter and multiply it by 1,000 to go from liters to cubic meters. So that'll be 10 to the 9th particles per cubic meter. So once we've done those conversions, again, a little bit involved just because the different unit conversions here, this omega then should be 1.26 times 10 to the minus 4. That is in cubic meters per cubic meter, so it's again a unitless fraction. And that then, when we put that into our equation for K, will finally give us K at a K value to be 6.63 times 10 to the minus 4 per second. Okay, and that's again where the per second is coming into play, which is why we went ahead and converted our time into per seconds. We could convert this per second right here into minutes, but I went ahead and just put the time into seconds. Okay, then if we put n at time 30 minutes, given that we converted it, then we put in our n naught, and if we want particles per liter, then we'll use this guy. I guess if we wanted to report n at 30 in particles per cubic meter, we could use this one here. That would be no problem. But I did ask for per liter, so we'll go with that. We'll go with the per liter here. So putting those numbers in, we would get a value of 1.14 times 10 to the 6 particles per liter. So if we compare that to what we started with, essentially, let's say 375 compared to 114, it looks like there's about 3 particles, something like that, of the new aggregated particles per liter, per initial particle, something like that. Okay, so then the next question is answering exactly what I just noted. What is the average number of single particles, those initial ones, and not per final particle after 30 minutes? So this was that 3.75 times 10 to the 6 divided by that 1.14 times 10 to the 6 particles per liter. And this is going to give us, if we do that calculation, 3.30 of the initial compared to the final particles. Part D then asks, what would the particle concentration be after 30 minutes if the particles were not completely destabilized and only 40% of the particles, particle collisions resulted in a new particle? So here we're changing one of the essential components. Maybe we missed the coagulation dosing, and this particular jar was not very effective. So this is asking us, okay, what's a new N30? Given that this collision efficiency is equal to 0.40. That's going to change the G. We'll have a new G, G is not going to change, the new K, because the new K, this was alpha, or this collision efficiency, times 4 times the omega, times G divided by pi. So with the new K, essentially it's 0.4 of the old K. This K is going to be 2.65 times 10 to the minus 4 per second. So we didn't have to do too many calculations. We could have even just taken the previous K and multiplied it by 0.4 for that. So we take this new K and put it into the equation just as we did a moment ago and say the new N30 is going to be 2.33 times 10 to the 6 particles per liter. So instead of 1.14 times 10 to the 6, now we have 2.33 times 10 to the minus 6. Or to the 6, right? By the way, earlier I just simplified that because they were both times 10 to the 6. I just got rid of that just for the sake of going through it faster. Okay, so then our last problem here, problem 4a. So the problem says, in order to keep a set of 3 Olympic swimming pools clean, granular filtration cartridge units are used. Each unit is cylindrical with a 1.25 meter diameter and 1.5 meter height. Each pool contains 2.5 million liters of water, and the filters must treat enough water such that the hydraulic residence time is 1 day for each pool. And to clarify, that says, the filtered water is recirculated back into the pool. Okay, so the filters are pressurized and operate at a high rate of 15 meters per hour during filtration and 25 meters per hour during backwashing. Of course, they're not putting backwash back into the pool. The filters are automatically backwash and rinse after 24 hours of filtration time, taking 15 minutes for each process. So, the first question is, what is the effective loading rate for the filters? And I ask you to answer in meters per hour. So this is REF, and we have an equation for that. It's given, and that's going to be, let's bring this over to show you. That's going to be our VF, so the volume filtered minus volume backwashed minus volume rinsed, divided by the area times the time. So that's VF minus VB minus VR divided by the area of the filter times the total cycle time. Okay, so let's draw one of these units. We have cylindrical units. So something like this. They are pressurized vessels, so they don't take up quite as much area. By the way, if you've ever been involved with any sort of pool maintenance, granular filters are indeed often used for them. Okay, so these guys are 1.25 meters in diameter, 1.5 meters high, and the volume of each pool is 2.5 million liters. So let's say that 2.5 times 10 to the 6th liters, and we have 3 swimming pools, right? We have, let's say, 3 Olympic swimming pools that are being treated, so we're treating water from all 3, and each of these has 2.5 million liters. So what I'm going to say is, we'll just say the total volume here would be 7.5 times 10 to the 6 liters. That would also, we could convert directly and say that 7.5 times 10 to the 3rd cubic meters. So I'm going to go ahead and convert that into meters. That's the total volume for of the swimming pools. Okay. Whereas this is one filter here. We don't probably need the height of the filter at all. That was just added to the problem. Probably considered a red herring. You don't really need it. The area of the filter, I guess maybe we'll need it if we do some sort of calculation with the amount of media we're using or something. So the area of the filter, though, that would be pi r squared, or pi diameter squared divided by 4. And so that will be a value here. Let's go ahead and calculate that. Let's say the area of a filter is equal to pi 141, do that, times diameter squared, which is 1.25, and all that divided by 4. So our area is 1.23. Square meters for each filter. Okay, then our cycle time, TC, is 24 hours. Let's go ahead and write out the time for the backwash, time for the rinse, and the time for the filtration. Because we're going to need all those to calculate the volumes. So the time for the backwash, that was 15 minutes. I'm going to go ahead and convert to hours and 15 minutes. Let's see. It says 15 minutes for each process, right? So 15 minutes for backwash and 15 minutes for rinse. There's no mention of air purge, so nothing to do with air in this system. So the backwash time is 15 minutes. Well, we know that you can divide an hour into 4 15-minute segments. So that's going to be a fourth of 1 hour, or 0.25 hours. So the time for the backwash is 0.25 hours. The time for the rinse, also 0.25 hours. And the time that is left for filtration over that 24 hours is going to be 23.5 hours, because we had to subtract those two parts. Okay, the other things we'll need to note are the loading rates. So VA for the loading, that was given as 15 meters per hour during normal conditions, and then during backflush, we have 25 meters per hour. Okay, so given that, we can then, calculate our effective loading rate, because now we'll have the tools to find our volumes. So let's find our volumes real quick. This is VB, VR, and VF. We have all the components here. So these are going to be, so the volume filtered is going to be that loading rate VA times the time of filtration, not the cycle time, the TF, times the area of a filter. Write that with an F there. Okay, so let's solve these. I'm going to write them out first. The volume of the backwash, that's going to be the backwash loading rate. And I'm trying to make these a lowercase versus an uppercase here. Hopefully that'll make it a little more clear. The volume for the rinse, we can find that by using the loading rate during the rinsing, which is VA. And the reason we use the loading rate for the rinsing rate is because we're rinsing at the same exact rate that we would be producing our water. So we're just operating in the same manner we would normally. Okay, so let's get Excel real quick and solve for these volumes. So VF, VB, and VR. So for each of these cases, we have that area. We're going to take that area and multiply it by, usually, so for the VF and the VA, that'll be 15 meters per hour. And then we'll multiply that by the amount of time we've got. So for the volume of filtered water, we have 23.5 hours. That's going to give us that many cubic meters. One thing I'm going to do here is lock the B4 there. Then I can fill this down and adjust the parameters inside as needed. So for the backwash, instead of a loading rate of 15, we use a loading rate of 25. And instead of 23.5, we have 0.25 hours for that. And lastly, this last component, we have the same loading rate for our rinsing has the same loading rate as normal, and then the again a quarter of an hour. Okay, so that gives us volumes of 432 and a half, 7.67, and 4.6 cubic meters for the volume filtered, volume backwashed, and volume rinsed. So with that, we can calculate our REF. That's going to be the total we produced minus the stuff that we used that had to be sent to waste. All that divided by the total cycle time, which was 24 hours, times the area of the filter. And with that, we get an effective loading rate that is a little bit below our production rate, which is what we would expect, 14.27 meters per hour. Okay, and one thing I'm going to do here just to make sure this is all written up here for everybody is write those in real quick. So this VF was 432.6 cubic meters. The backwash was 7.67 cubic meters, and the rinse was 4.60 cubic meters. Okay, so that's it for part A. Part B says how many filtration units are required to keep the pools clean. So that essentially what we're going to do there is take the total flow that we need to meet some total flow. That was essentially in the problem statement, it said we need to have a hydraulic residence time of 1 day. So essentially we need to flush that entire volume of all three pools once every day. So that means we take that 7.5 times 10 to the third cubic meters and take that many cubic meters every day. So that's going to be, if theta equals V over Q, then Q equals V over theta, and we were told that theta is essentially 1, so that is going to be equal to 7.5 times 10 to the third cubic meters per 1 day, and that's our flow rate, right? So cubic meters per day are our units. So that's our total flow, and we have to meet this by some number of filters. And those number of filters are going to provide us, we'll say, each filter is going to give us an effective loading rate. So we'll have a number of filters. We can multiply that by the amount of water effectively produced per filter, which is that REF. That's going to be in meters per hour. So we're going to multiply that by the area of one filter. So that'll give us go from meters per hour to cubic meters per hour. And of course, we need to convert from the hour terms to, so this will be meters per hour, and we need per days to match with the flow rate. And so we'll have to multiply this by 24 hours per 1 day. So that should give us our answer then. well, we'll solve this equation here for the number of filters, right? So the number of filters equals the Q total divided by the R effective times the area of a filter times 24 hours per day. Okay, so that'll give us 7.5 times 10 to the third cubic meters divided by that effective, which was 14.27, oops, meters per hour, multiplied by the area of the filter, which was 1.23 square meters, multiply that by our 24 hours per day. So that gets rid of our hours there. And we're left with cubic meters on top, cubic meters on bottom, per day on bottom. This should be cubic meters per day there as well. So the units should all cancel out nicely that way and give us just a final value here. So when we do that calculation, let's do that together real fast. This is going to be, I'll go ahead and write it out as, I'll add the 3 digits there. So 7,500 cubic meters per day. That's our flow rate divided by 14 point, well, let's go ahead and use that term, times the area of the filter, calculated there, times 24 hours per day. And that gives us that many filters. And what we need to do from this point, so 17.8, sorry. So 17.8 is the answer, but we can't have 0.8 of a filter, so we have to convert that, round it up. Even if the number was like 17.1, we'd still have to round up, and that gives us 18 filters. Okay, the final question is, what is the filter efficiency for these units? And that's simply our equation there. And we have an equation for that and pretty much all of the pieces in place already. So the filter efficiency is going to be the volume filtered minus the volume wasted divided by the volume filtered. So essentially the amount of usable water divided by the water, I guess the filtered water. Which is VF minus VB minus VR divided by VF. And this is a fraction. Of course, we could multiply it by 100 to get a percentage. So we have all of these. We'll call that nu. And that is equal to that volume filtered minus the volume backwashed minus the volume rinsed. All that divided by the volume filtered. So our filter efficiency is 97.2% or 0.972. Technically, this is the correct form, but if you wanted to conceptualize it like a percentage, that's no problem at all. Okay, so that's it for today. Again, I still only see one person attending live, so if you do have any questions, let me know. Be happy to talk through this when I pass back the exams, any issues that you had during that time. Okay, so with that, have a great weekend. And bye for now.